It's okay. Okay, so thank you for inviting me to have a talk here about energy efficiency in the production of pharma-grade water. Well, I will try to go through my slides like a German Porsche, so maybe then we can keep the time. Okay. This is the contents of my presentation. So at first I will stress the background of my talk. So what is the role of the pharmaceutical industry in terms of energy demand and the carbon footprint decarbonization. Then I will touch a little bit the techniques that are now being used for the preparation of pharmaceutical grade water, and then I will shortly touch also a topic of our research in the last years from the newer approach to produce pharma grade water with a lower impact on the environment. Okay, so at first I have to stress that the pharmaceutical industry has, like everything, two phases. So on the one hand side we have the pharmaceutical industry that serves the people, and on the other hand we have the same industry that is releasing not only carbon dioxide and so contributes to the climate change. And on the other hand we have the climate change that influences people's health. So we have two things that we have to put together in the future. And to give you an idea of the importance of these things that I'm talking about is that we have about 4.4 of global greenhouse gas emissions coming from the pharmaceutical industry. We have, if we take the example of the total emissions and compare it to countries, so then we can see that the worldwide pharmaceutical industry would be the fifth largest emitter of greenhouse gases. We can say that the three largest emitters in terms of countries, United States, China, and European Union, they are responsible for more than 50% of the world's total healthcare climate footprint. And together, all the first 10 healthcare emitters, that means the countries, make up 75% of the global climate footprint in this sector. So that means we have a strong need to work on this, and we have a strong impact if we can influence more environmentally friendly processes in the pharmaceutical industry. So, and to give you an idea of what is needed in the future to come to a more sustainable production, we don't only have to focus on the product water requirements. That's what we are normally focusing on in the pharmaceutical industry, compliance with the Pharmacogenomics. We also have to take into consideration the water availability in the respective countries, the water demand of the respective facilities, economy in any case, and what will be my focus, so the energy demand also of these processes, because energy is closely related, or energy production is closely related to the release of greenhouse gases. Well, and we have a lot of energy-intensive steps in the production of pharmaceutical products, and I will stress especially the processed water that finally ends up with purified water or with the water for injection. So here you can see different technologies that are employed. So membranes for desalination are most importantly used in desalination, not only for the pharmaceutical industry, but also for the pharmaceutical industry. You have thermal processes and others. If you count, put these numbers together, you can see that others are hardly existing.
Desalination is different from ionizer, deionized and purified or distilled?
No, the main idea, so coming from different, let's say, industries, sometimes we say desalination, sometimes deionized water. The main idea is the same, but the concentrations that we achieve in the final product are certainly different, because in the pharmaceutical industry we have different demands in the energy production, we have different demands for clean water. So this is a broad technology, bundle of technologies, and with specific aims in different industries. Well, in Europe we have the European Pharmacopoeia, and this contains the official quality standards for the pharmaceutical products, including certainly also water. So there's a restriction, as you also have in your respective countries. So for the purified water, this is the technologies that are allowed to be used is reverse osmosis, is distillation, it's ultrafiltration, ion exchange, and electric deionization. And in most cases, you have to add different technologies, put them together to achieve the final product. So for water for injection, we have the highest quality standards, and this is, according to the European Pharmacopoeia, only allowed by using distillation. So here it's a strong focus on distillation. Distillation, on the other hand, has a big problem with the energy demand. Yeah? Whereas while reverse osmosis as an alternative is now the best option in terms of energy demand, but maybe not of quality. We have the problem with the distillation that has a high energy demand that is far away from the energy demand of the membrane technologies. So several times larger energy demand. Well, and here I come to reverse osmosis, just to give you an idea. So reverse osmosis is using so-called dense membranes, so that means they are completely dense, no holes or pores inside, so that the liquid that passes through the membrane diffuses through this structure. And because this structure is so dense, unlike the coffee filter, we need more pressure and to press the water through, and the dense structure prevents ions or small organic molecules from passing through the membrane. So that's the main idea. And by rejecting the ions, we exceed the concentration, and the higher concentration leads to osmotic pressure. And this works in the other way. That means in this direction. So therefore, to press water or to produce water of any quality by reverse osmosis, we need to have a higher pressure than the osmotic pressure that is prevailing here. Well, and here you can see a typical setup. So this is from water production, but the same setup is in principle possible for pharmaceutical grade water. Well, then we have distillation in different setups. So in order to achieve higher efficiency in terms of the energy demand, we normally work at a specific pressure in several steps, so that the pressure is released, and at the same time the evaporation point will be sinking. And so by such a stage process, we can achieve the best available, or the best possible results also in terms of the respective energy demand. So feed temperature is normally in the range of 100 degrees, and if we decrease the pressure, so then we can also decrease the respective temperature that is required for achieving the specific water quality. So another step was done with the so-called multiple effect distillation. So here we can work with specifically lower temperature, so that means in general the energy demand is lower compared to other processes. And then we have ion exchange. Well, it's working with specific synthetic resins, so resin beads, small particles, and water is going through, and certain components, especially the ions, they are absorbed. And after a given time, the ion exchanger is reaching its capability to reject more substances, more ions, and then the regeneration has to take place. So this process is not a continuous one, it's a batch-wise process, which is kind of disadvantage, and you need chemicals for the regeneration of these ion exchanger materials. So here you can see the combination of membranes with ion exchangers. So that's the CDI or EDI or whatever it is called. It uses electricity, membranes, and ion exchangers to achieve a certain water quality, and this is also quite commonly used in the industry. So another approach that we were working on is to use membrane distillation. So membrane distillation is using different membranes than reverse osmosis. So in this case we have hydrophobic microfiltration membranes or ultrafiltration membranes. These membranes, they have pores. So from one side to the other side. But because these membranes, they are hydrophobic, water cannot pass through these channels or through these pores, only the vapor can. So, and then with the help of this process, we can use the evaporation step here for achieving clean water. The advantage of membrane distillation is that it can be operated with the help of low temperature waste heat. So that means a waste heat that otherwise cannot be used. But here in this process, it's a good temperature. When we have waste heat under 100 degrees, it can be applied. And another advantage is that we can achieve a higher productivity compared to the conventional distillation process. So when the steam has passed through the membrane, certainly we want to achieve a liquid, so that means we need to cool it down to condensate it again, and so then this is applied here in such a setup. Or
sorry, Professor, it is now the time for 5-minute alarm.
Yes.
Okay.
Okay. Here you can see our specific setup. So this was done by the German company Werner. They are active in the field of pharmaceutical grade water, and this is such a module where a multitude of these membranes are inserted. So several chambers are included in this module in order to achieve a higher membrane area. Well, and here are some results. So in principle, I can cut it short. So the higher the temperature of the feed solution is, the higher will be the productivity. The productivity will also be higher when we have a higher coolant velocity. So that means that more vapor can be condensated. And the third effect is that we also need to have a certain velocity of the the water to be treated parallel to the membrane. So the higher the velocity, also the higher is the respective volume flow of the steam. Well, these are some results from long-term trials. So the rejection of salts was always larger than 99.5%. So what is more important than the salt rejection is certainly the biological related problems. So we measured the total counts of the bacteria, and we saw that within our distillate, in our setup, we could reach 300 colony-forming units and compared them to the water for injection and with purified water. So it was not possible to achieve the requirements for water for injection, but it was possible in any case to achieve the limiting value here from the purified water, so 300 CFU and 10,000 CFU. So there's a big difference. So the quality can be achieved that is required for producing purified water. Still there's a problem. So with our setup, the energy demand was not that good as we expected compared to the distillation technologies that are already introduced in the pharmaceutical industry. If you compare it to reverse osmosis, we have a factor 10 or so smaller. So I did not put it in this table because then our number looks a little bit ridiculous. So with other words, there's a lot of efforts that need to be done in order to establish this procedure, to find better ways of using fewer energy, and maybe also to come to better biological qualities in the final product. Well, do you have any questions? Please feel free to ask.